7.6 Precipitation reactions. We talked real briefly about these at the beginning of the chapter. A precipitation reaction is where you mix two liquid solutions together and you get a solid that forms. An example of this is sodium carbonate, which is an ingredient in your laundry detergent. It reacts with dissolved magnesium and calcium ions that are present in hard water, and it forms solids that precipitate out of solution. So it's going to make magnesium carbonate and calcium carbonate, and it'll precipitate those out, and those will get rinsed away with the water so that the calcium and magnesium do not precipitate with the soap instead and make that yucky, slimy, gray stuff that gets on your clothing. So that's an example of a precipitation reaction. Reactions that form a solid. The solid is called a precipitate, and that's related to the way they use it in meteorology. A precipitation is snow, sleet, rain, hail, stuff falling out of the sky. Here's a picture. Potassium iodide solution mixing with lead nitrate solution. You get this brilliant yellow precipitate of lead iodide. And when we look at the equation, we see that both of the reactants are aqueous, meaning they're dissolved in water. And this product, Pbl₂, is a solid. And if you look that up in the solubility rules, you'll see that it's insoluble in water. And that's why we list it as a solid. And that potassium nitrate is aqueous because it is soluble. And so our equation is a description of what actually happens. What actually happens is you mix those two things and you get this yellow solid that forms. Now, if you mix two aqueous solutions of ionic compounds, you do not always get a solid forming. So in this example, we've got potassium iodide and sodium chloride. Both of those compounds are soluble. When we mix them, the possible products, let's see, I'll write it over here. So we've got potassium ions, and we've got iodide ions, and we've got sodium ions, and we've got chloride ions. So the potassium came in with the iodide, and the sodium came in with the chloride. If there's going to be some sort of precipitation, they're going to have to switch partners, and we get potassium and chloride together and sodium and iodide together. And you can look those up in the solubility rules, and you see that sodium iodide is soluble and potassium chloride is also soluble. So when you mix these, no solid forms because everything is soluble. Okay, so just because you're mixing two ionic things does not mean that you're going to end up with a precipitate. We need to learn how to predict precipitation reactions, and I think those are most of the reactions on that equations worksheet that you need to do. So this is important. When predicting precipitation reactions, only insoluble compounds form precipitates. So if you have a precipitation reaction, you have two solutions with soluble compounds, and those are going to combine and form an insoluble compound, which will precipitate or fall out of solution. If it doesn't form a solid compound, you just have two solutions that mixed, and it's not a chemical reaction, it's just a physical change of mixing. So let's look at what happens when potassium iodide and lead nitrate are mixed. So before mixing, in this beaker, we have potassium ions and we have iodide ions, and they separate when they dissolve in water. This is a strong electrolyte. It dissociates into its ions. And in this other beaker, we have the nitrate ions, which stay intact because that's a polyatomic ion. They're like shrink-wrapped together. And then, where is it? There's the lead ion. So those are going to be separated. So that's what you have before you mix it. Immediately after you mix it, now you've got all of those same ions together in one beaker. And so we need to look at what are the possible combinations of ions. Well, let's go back and do. So one way to look at this is to make a little table. So we have potassium ions, and we have lead-2 ions, and we have iodide ions, and we have nitrate ions. So what are the possible combinations? Well, you have to have a positive and a negative. You can't combine two negative ions or two positive ions. So we could have potassium with iodide, which would give us Ki. We could have that's lead with iodide, and that would be Pbl₂. We could have potassium with nitrate, or we could have lead with nitrate. Those are the possible combinations between those four ions. So I've told you before, I think of the metals as being masculine and the nonmetals as being feminine. So the cations are like the guys, and the anions, the nonmetals, are like the girls. And so here we have two guys and two girls, and what are the possible combinations between them? When we look at these, we see that two of these are the reactants, right? This is a reactant, and this one's a reactant. So could those form a solid? No, because they were soluble. They were dissolved to start with. When we mix them together with something else, they're not going to suddenly become insoluble. They're still going to be soluble. So if we see a solid forming, it can't be one of those things. Those were the reactants. So the products must be these other guys. So this is a potential product, and this is a potential product.
Sorry, why was the calcium iodide not, and the lead nitrate, why was that not allowed to, why were those listed as insolubles originally?
They're soluble.
Sorry, solubles originally?
Because in our original, we had a solution of potassium iodide, and if you go look potassium iodide up in the table, it is soluble.
Okay.
And we had lead nitrate. And so that was kind of given to us that those are both aqueous, and they're listed up here as well.
Oh,
so
okay.
Here. So that's what we started with, those dissolved in water. If we mix them together and a solid forms, we're trying to figure out, well, what's the solid? It can't be one of the things we started with because we've already seen that those were soluble.
Okay.
So it has to be a different combination, either this one or this one. So we could look these up in the table and see which one is, or maybe they're both insoluble, that's possible. So if we look up lead iodide, we find out that that's insoluble, so that's going to be a solid. If we look up potassium nitrate, we're going to see that that one is soluble, so that one's going to be aqueous. But when you have four ions, you have four possible combinations between them.
So if neither of those, if both of those were soluble,
Mm-hmm.
we wouldn't need the chemical reaction, we just have
Right.
swimming ions.
Right. If both of these potential products are soluble in water, then we don't have a chemical reaction. We just have a mixing of two solutions.
Is that saying if they were to come back out of solution, they'd come back out as the same ionic compound?
So if we took this mixed up solution and evaporated the water, would we end up with our original compounds back? No. Not necessarily. You could end up with any of the four.
So would that make, then it would be chemical reaction then after you took out the water?
That's a real good question. Would that be a chemical reaction if you had this mixture of soluble compounds and then you evaporated the water?
Is evaporation not a chemical reaction because it's just water changing forms?
Well, the water evaporating is definitely just a physical change. But if you're removing the water and ending up with something that's different
When you start off.
is, yeah. I really wouldn't call that a chemical reaction. I really wouldn't. I don't think I can give you a satisfactory answer for why that is not, though.
Okay, what about if you, when you're mixing those chemicals together and we don't get a physical reaction from it, in the sense of an insoluble being created, but the chemicals together are now, they react in the sense that they become toxic, or because they have now combined in a toxic solution where one is now lethal. One inert versus two inert compounds, and now they mix together, they become an incredibly toxic solution.
If you had these two non-toxic things combining and forming a toxic thing, there would be some, maybe not a precipitation reaction, but some other type of reaction that would occur. And there are definitely other types of reactions that could occur when you mix these things. But right now we're just talking about precipitation reactions. That's a good question. So if both of these were soluble, we would say there is no reaction. And if you don't want to write that all out, the accepted abbreviation for no reaction is capital N, capital R. NR, no reaction.
That's if both are insoluble? Or?
If both of them are soluble. If both of the potential products are soluble, there's no chemical reaction. It's just a physical mixing. Has it changed? Yeah, it's a physical change, but it's not what we consider a chemical change.
Are you listening to S as solid, right? As insoluble?
Yeah, S here stands for solid.
Making sure. Okay.
Yeah, it's a little
Insoluble.
confusing. Is S for soluble or S for solid?
Are you sure?
S is for solid. Yeah, we don't usually use abbreviations for soluble, insoluble. So this is an illustration of what happens. The lead ions and the iodide ions, when they come in, close proximity to each other, they combine to form a compound that is not soluble. And so they'll precipitate out. What happens to the nitrate ions and the potassium ions? They're just left floating about. And so here's my stupid analogy. The stupider they are, the better. So you imagine two guys and two girls, and they're going to a party, and they go as couples. And so we have lead and lead and nitrate went as a couple, and potassium and iodide went as a couple, and they go to this party. And they get to the party, and they don't just stay right next to each other the whole time. They move about the house or whatever, and they mingle, right? And then lead runs into iodide, and he thinks that she is really, really fine, and she likes him too. And they just have this chemistry, right? And they just like each other so much. And so later on in the party, you're like, where did lead and iodide go? Well, they're on the back porch making out. They're not mingling anymore. They're off. They settled out. They precipitated out. They're stuck on each other. Okay? Does that help? A little bit? Can you imagine that happening? And so the other poor two, the potassium and the nitrate, what are they going to do? Well, they're just like, well, we can't do anything about that. Let's just enjoy the party. And so they're just mingling about and having a good time. So this is a precipitation reaction. What happens is you had two compounds that come in, and they're both soluble. They're going to mix at the party. And as they're mixing, one of the cations and one of the anions, when those two get together, they form an insoluble compound. And so they're not going to mingle anymore. They're just going to settle out as a solid, and a precipitate will form. The other ions will just be left in solution, mingling about. Okay.
So when we write this equation down in our equations, would we leave the potassium and nitrate together or separate?
It depends on the type of equation. Usually it's going to be together. The difference, though, is that the Pbl₂ has S for solid, and the KNO3 has AQ for aqueous.
So we would
And so when we see aqueous, we understand that that means that those ions are swimming around in the solution. And when we see solid, we understand that those ions are as a compound sitting in the bottom of the beaker.
And when we are balancing it, does that mean we don't have to balance the second compound?
We'll look at that. What we'll find is that we can actually treat those polyatomic ions as units and balance them without considering all the individual elements in them. But yes, we do have to balance all the ions. So here are steps for writing equations for precipitation reactions, and this is what's going to help you do that worksheet. First of all, write the formulas of the two compounds being mixed. Then below the equation, write the formulas of the ions. Okay, so this kind of goes back to Chapter 5 nomenclature stuff. You have to be able to write the ions with their charges. And then you're going to swap partners and see what happens. Okay? So, maybe they're out on the dance floor and it's like, can I cut in? And they switch partners and to see what happens. And if these two really hit it off, if they're insoluble, then that's your solid. So we'll exchange the ions and rewrite the formulas above that, and I'll do some examples. Then you use the solubility rules to see if either of those new pairs of ions is insoluble. If one of those is insoluble, you have a solid. If they're both soluble, if they're both going to be aqueous, then you can stop and just write NR, and you don't have to balance it or anything. Oh, yeah, if both pairs are soluble, right, no reaction. I really cannot see into the future, but sometimes it appears that way. So if either of those new pairs is insoluble, you write S for solid, and you use AQ to indicate the one that's soluble. Then, after you've written those correct formulas and identified their states, then you balance it using coefficients and don't touch the subscripts. Okay? Do some examples. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium hydroxide and nickel-2 bromide are mixed. Now, on that worksheet, you're actually given the formulas for the reactants, so it's a little easier. But we're going to sneak in some review of nomenclature. So, potassium hydroxide. Well, these, and here's a tip. In these precipitation reactions, it's all ionic compounds. So you don't have to think about that too much. So potassium hydroxide. Yeah. So potassium is K+, and I didn't want that color. Potassium is K+, and hydroxide is OH-. And so these together are going to be KOH. And it tells us that we have solutions of these. So we don't have to go look them up in the table. They are solutions, therefore they must be soluble, and we put AQ. And then nickel-2 bromide. Well, nickel-2 is Ni2+, and bromide is Br-. So this is NiBr2, and that's also aqueous. So usually, like on an exam, I'll give you the formulas and just ask you to predict the products. And what the steps we're saying is put the formulas in first, and then write these ions with their charges below. If you're not given them, you're going to have to look at the ion charges first before you can write the equations for those guys. But now what we're going to do is we're going to swap partners. So potassium is going to dance with bromine, and hydroxide and nickel-2 are going to dance or meet up at the party. So then over here, again underneath, I'm going to write the formulas for these ions. So I've got potassium, and I've got bromide, and I've got nickel and hydroxide. So hydroxide and nickel. I'm running out of space again. You have to write the formulas with their charges. So then I'm going to look at the charges so that I can write the formulas for the products up here. KBr, I'm going to leave a blank there, and NiO2. And here's its space. Yeah, I ran out of room. Now we have to go to the table of solubility rules and find out if either of these is insoluble. If we look up potassium bromide, we see that potassium compounds are generally soluble and there are no exceptions. So this is AQ. If we look up hydroxide compounds, we're not going to find nickel listed as generally this or that, but we'll find hydroxide. We'll find out that hydroxide compounds are generally insoluble except for certain things. This is not one of the exceptions. And so this is going to be solid. So you swap the partners, you write the new formulas, and then you have to balance the equation.
So nickel hydroxide is what?
Pardon me?
So nickel hydroxides are actually insoluble.
Nickel hydroxide is the solid that's forming. Yes, that's the precipitate. Yep. You got to precipitate, so then you have to go ahead and balance the equation. So do you notice that the hydroxide is present on the left and on the right as hydroxide ion? It didn't come apart, it didn't change. These polyatomic ions, you can balance them as a unit because they're not coming apart. If you prefer to balance all of the elements individually, you can also do that, whichever approach works for you. I'm going to balance polyatomic ions as a unit. So I look on the left side, I have 1 potassium. On the right side, I have 1 potassium. On the left side, I have 1 hydroxide. On the right, I have 2 hydroxides. See, I've got 2 right here, right there, 2 of them. So then I need to put a coefficient on the left side so that I can get 2 hydroxides on the left. I've got 2 hydroxides on the left, 2 hydroxides on the right, but I messed up the potassiums that I had already considered. So I need to make there be 2 potassiums on the right side. So now I've got 2 potassiums on each side, 2 hydroxide ions on each side, and then let's look at the other guys. Nickel, there's 1 nickel on the left and 1 nickel on the right. There's 2 bromines on the left and 2 bromines on the right. So this is our balanced equation. Any questions? Yes?
How do you know that the hydroxide and the nickel go together and the potassium and the nickel?
Well, because here we have, this is a guy and this is a guy. And I'll just make down arrows. Actually, let's just do plus and minus. So here we have a positive ion and a negative ion, and a positive ion and a negative ion. Okay, and this is going like traditional. Okay, this is not San Francisco. It's traditional. So we've got a guy and a girl, and a guy and a girl. Okay. Because it's positive and negative charges. 2 positive charges are not going to be attracted to each other. And so you can't have potassium with nickel because like charges repel each other. You can't have hydroxide with bromide because those negative charges repel each other. So potassium only has 2 possible partners, the one he came with and the one that the other guy came with. So obviously he didn't have this super reaction with the one he came with because they dissolved in water. They mingled at the party. They didn't just go straight to the bedroom or whatever.
They're cheating atoms.
Pardon me?
They're cheating atoms.
Cheating atoms, yeah. Well, they're uncommitted. They're uncommitted atoms. It's like, this isn't an exclusive relationship we're in here. We're just, I didn't want to go by myself, so hey, you want to go with me? A guy and a girl, they go to a party, they're like, yeah, I like you, but, you're not the dream person, right? So they go and they mingle, and they're kind of hoping to meet somebody else. It gets really strange. Anyway, so that's why there's only 2 possible products, because it can't be one of the reactants. Does that answer your question? It's a good question. I always get people on an exam trying to put two guys together. Well, in real life, you are welcome to do whatever you want, but this is positive and negative charges. And play with the Pbl₂ trains and try to put those trains together backwards. They're not going to stick. They just will not stick, okay? And no amount of talking or rationalizing will make them stick. Any other questions? Here's another example. Write an equation for the precipitation reaction that occurs, if any, when solutions of ammonium chloride and iron 3 nitrate are mixed. Let's see if I can make this fit this time. So ammonium chloride. Ammonium is NH4. It's yellow, who cares? And chloride is Cl minus. If you are still struggling with concepts like this, please talk to me. So those together would be NH4Cl. These are solutions, so we know that these are aqueous. Plus, I'm going to leave a little space there in case I need to put a coefficient. Iron 3 is Fe. The Roman numeral 3 tells us it's a 3 plus charge. Nitrate you have to memorize, NO3 with a -1 charge. We look at those charges, plus 3 minus 1. They're not the same, so you can do the crisscross thing. So Fe, NO3, 3, and this has to be aqueous because it's a solution. Now we're going to swap partners. These two and these two. You find a way to remember this. It's like, okay, well, I take the outside ones together and the inside ones together, or whatever works for you. And the order that you put them in as products doesn't matter. If I put it as the first product and you put it as the second product, that's okay, as long as you have the combination correct. So NH4, we're going to see if he gets along with NO3. And Fe, 3 plus, we're going to see how he gets along with chloride. So you could save yourself a little bit of work by just checking these out for solubility right now. Ammonium and nitrate, if you look those up in the table, they both form soluble compounds with no exceptions. Okay, so we look this up in the table. And let's see, chloride compounds are mostly soluble, except with silver, mercury, or lead. Well, we've got iron. So this one is aqueous, and that one is aqueous. So we've got a big old NR, no reaction. They mix, but nothing happens. So these two couples come to the party, they mingle around, and nobody meets the love of their life. Nobody ends up making out. Okay, so this is, yeah. So here's another one. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium sulfate and strontium nitrate are mixed. So again, you're going to write these ions. Potassium sulfate. Got to press the annotate button first, then write the silly ions. Okay, K plus, sulfate is SO4, 2 minus. So when those two go together, we've got K2SO4. And we know the state is aqueous because we're told that's a solution. You could look it up if you want to. Strontium nitrate. Strontium is Sr. What is the charge on strontium ion? There's no Roman numeral. Periodic table, in column 2, it's got a 2 plus charge. And nitrate is NO3 minus. So this formula is Sr, NO3, 2, and this is aqueous. Now we're going to swap partners and see if there's any chemistry. Interestingly, my husband and I met the first day of graduate school. We're both chemists. We both were in graduate school for chemistry.
And you had chemistry?
It was chemistry. We did have chemistry. It was like, ooh, interesting. Like him. Yeah. So we switch these partners here. K plus and NO3 and SR 2 plus and see, I'm blanking. I can't even remember. So we saw on the last one that sometimes you can save yourself a little work by checking the solubility rules first. So let's check these before we actually write the formulas. Potassium compounds, mostly soluble. Nitrate compounds, mostly soluble. So this one's soluble. It's going to be aqueous. Strontium sulfate. So sulfate compounds, mostly soluble. When under exceptions, it says when sulfate ion pairs with strontium, blah, 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 the compound is insoluble. So strontium sulfate is a solid. So we have to finish this one out. So potassium and nitrate, each is +1, -1. So they're like that. And strontium sulfate, +2, -2, SrSO4. That's a solid. And now we need to balance it. We've got our product, and so we balance it, and we look at potassium. On the left side, there's 2 potassiums. On the right side, there's only 1. So we'll put a 2 in front of KNO3. That's an ugly 2. What? There we go. So 2 potassiums on each side. We have 1 sulfate. Sulfate's a bundle pack, okay? It's stayed together. It's still sulfate on the other side. We have 1 sulfate on the left, 1 sulfate on the right. We have 1 strontium on the left and 1 strontium on the right. And we have 2 nitrates on the left and 2 nitrates on the right because we have that coefficient of 2. And so there it is balanced. These precipitation reactions are generally very simple to balance. If they're not easy to balance, then check your formulas, because if you get the formula wrong, it's going to be impossible. Any questions?